Okay, so we will start at 3. It's 2:59 right now. Okay, so it's 3 o'clock, so we can go ahead and start now. So today we will be starting our last chapter for this course, which is particle properties of waves. Okay, so we'll be starting off by we'll discuss about electromagnetic waves and the classical perception. Okay, about classical physics, and then we will talk about electromagnetic waves. And we will talk about what are the properties of these waves. To get properties of waves, we'll talk about interference, diffraction. Then we will go into black body radiation. Okay? And we have to do all of this and then we will do some examples. We'll do Planck's formula, we'll do the Rayleigh-Jeans formula, and we will do some examples related to black body radiation. So to start off, we'll talk about classical physics. Okay? So classical physics, what do we mean by classical physics is similar, like classical physics is what we can see like in our reality, okay? In a sense that it treats particles and waves as separate components of that reality, okay? So basically classical physics we have two different particles are independent and waves are independent, okay? They're two separate entities and they're not related to each other, okay? But in non-classical mechanics like quantum physics, etc., particles can have wave-like properties as well. And we have already done the wave properties of particles. Okay? We have already done that chapter. So this is basically combined the wave properties of particles and the particle properties of waves. They are basically part of the wave-particle duality. Okay? So we'll be talking about that. That comes more under quantum. Okay? The classical physics is different from that. Okay? So classical physics treats particles and waves as two separate entities, two separate components of our reality. So the mechanics of particles and optics of waves are traditionally independent disciplines. Okay? So we have particles जिसकी mechanics होती है ना, like उनकी collisions होती हैं, उनके velocities होती हैं, momentums होती है, momenta होती हैं, ठीक है? They have momenta, they have velocities, they have masses, and etc. And we can understand their trajectory of the particles as understand its motion, their velocities, their accelerations, etc. Okay? So that is all part of the mechanics of particles. Now the optics of waves is independent, totally a different topic in classical physics. Okay? Classical physics optics of waves is totally different from the mechanics of particles, each with its own chain of experiments and principles based on the results. Okay? So the mechanics of particles and the optics of waves, they're two independent disciplines, and each of them have their own experiments which prove the theories and principles that are based on the results of the experiments. Okay? So electrons in classical physics, we regard electrons as particles because they possess charge and mass and behave according to the laws of particle mechanics. Okay? So basically electrons, according to classical physics, they are particles because they have charge, they have mass, they can have a velocity, they can have a certain velocity or acceleration, and they can experience forces and all those different things. So we can see the trajectory of the electrons as well. We can understand that as well, and its motion. So basically electrons in classical physics are regarded as particles. ठीक है? They behave according to the laws of particle mechanics. ठीक है? जो हमारे पास mechanics होता है, Newton's laws of motion and other mechanics, ठीक है? That applies to particles like electrons. So we shall see that it is just as correct to interpret a moving electron as a wave manifestation as it is to interpret it as a particle manifestation. So basically, with the revolution that came during Einstein's time, ठीक है? We were faced with wave particle duality, ठीक है? That was discovered, ठीक है? Wave particle duality was discovered during Einstein's time. And so basically in that we can say now we know that it is correct to say that electrons can have a wave manifestation or a wave nature as well as a particle manifestation, ठीक है? So we're going to go into that in this chapter. We're going to go more into those details as to how we can say that that is correct. So electromagnetic waves are waves because we regard electromagnetic waves as waves because under suitable circumstances they exhibit diffraction, interference, and polarization, ठीक है? So these are some properties of waves. They exhibit diffraction. Diffraction is one particle we're going to study about, do a little bit of that. We will do interference, which is a property of wave, and polarization. Does anyone know what polarization is? Polarization is also another property of wave. Like we know that electromagnetic waves has electric fields and magnetic fields oscillating at right angles to each other, right? You have already studied courses on electromagnetic theory, okay? So basically, it has oscillating electric fields and magnetic fields are oscillating at right angles to each other, okay? And that is also perpendicular to both of these two. The direction, if this is the direction of the magnetic field, this is the direction of the electric field, then this is the direction of the motion of the electromagnetic wave, which is obviously all three of these directions are perpendicular to each other. Okay? So polarization means like if the wave is polarized like this in this direction, okay? Or if the electric field is polarized in this direction, or if it's like what electromagnetic waves, sometimes we have a beam that is either polarized or unpolarized. If it's polarized, then the electric field will be in a particular direction and all the light waves in the beam will be in a particular direction. Okay? Are you all familiar with polarization? And the magnetic field would be similarly in this direction. Okay? It's hard to draw it over here because it's three-dimensional. But if we have an isotropic, like unpolarized wave, then we would have electric fields in all directions, okay? It would be unpolarized. So polarization is one example, one property of a light wave. So similarly, we see that under circumstances, electromagnetic waves behave as though they consist of a stream of particles. So what we're saying here is that diffraction, interference, polarization are properties of electromagnetic waves. They're properties of waves, but we will see in this chapter that under certain circumstances, electromagnetic waves can behave as though they are consisting of particles as well. So that is the particle properties of the waves. Okay? So in 1864, the British physicist James Clerk Maxwell made the remarkable suggestion that accelerated electric charges generate linked electric and magnetic disturbances that can travel indefinitely through space. Basically, we know about electromagnetic waves that they have electric fields oscillating along in one direction sinusoidally, okay? Sinusoidally, and we have magnetic field that is oscillating at right angles to the electric field, also sinusoidally, okay? So this is and also these both are the direction of the electric field and the direction of the magnetic field and the direction of propagation of the wave. All three are perpendicular to each other. So from the earlier work of Faraday, Maxwell knew that changing magnetic field. So basically, we know that changing magnetic field can induce a current in a wire loop. आपने electrodynamics में पढ़ा होगा ये कि if we have a changing magnetic field, it can induce a current in a wire loop. ठीक है? So changing magnetic field is equivalent to its effect on an electric field. So why are we discussing this? Because these are certain properties of electromagnetic waves and how we can understand these waves as well. So Maxwell proposed the converse: a changing electric field has a magnetic field associated with it as well. Okay? So Maxwell and Faraday, they both contributed to electromagnetic waves and electrodynamics. Okay? So there are some important scientists in this area. So basically, they proposed that we can have a changing magnetic field can induce a current in a wire loop, and changing electric field has a magnetic field associated with it. So basically, the electric field and magnetic field can be related as well. So Maxwell was able to show that the speed of electromagnetic wave, basically we know the equation for the speed of electromagnetic wave, which is given by c is equals to 1 over square root epsilon naught mu naught, okay, which is approximately equal to 3 to 10 raised to power 8 meters per second. And this is the speed of the light, the value that it takes. And if you plug in the values for epsilon naught and mu naught into this equation, you will get the speed of light. So basically, epsilon naught here is electric permittivity of free space, and mu naught is the magnetic permeability. So basically, the electric property of the wave is coming in this term, in this variable, in this constant. Sorry, not variable, it's a constant. And the magnetic part of the wave comes into this term, into this constant. Okay? So this so basically this is some properties of electromagnetic waves. And then during Maxwell's life, the notion of electromagnetic waves, we did not have experimental support for electromagnetic waves, but in 1988, German physicist Hertz showed that electromagnetic waves do exist and behave exactly as Maxwell had predicted. So basically, during Maxwell's time, electromagnetic waves do not have direct experimental support. Experimental evidence नहीं थी उस वक्त. बाद में 1888 में Hertz ने he proved that the waves, electromagnetic waves, do exist and they behave as Maxwell had predicted. So Hertz determined the wavelength and speed of the waves he generated, show that they have both electric and magnetic components. ठीक है? So Hertz ने basically determined किया था कि जो electromagnetic waves हैं, they have both electric and magnetic components. ठीक है? And he also determined the speed of the electromagnetic waves, as we found over here, as we know that it's like given by this formula and it has this value. So Hertz also found that electromagnetic waves could be reflected, refracted, diffracted. So certain properties of waves include reflection, refraction, diffraction, interference, polarization. These are some properties of electromagnetic waves. Not just of electromagnetic waves, but waves in general. Okay? So these are properties of waves. So light is not the only example. So right now we're just doing a theoretical aspect of this chapter, and then we're going to go into calculations and soon. Okay? So light is not the only example of electromagnetic waves. Basically, we have also the electromagnetic waves. The electromagnetic waves have a wide spectrum of frequencies. Okay? Have a wide range of frequencies and wavelengths. So basically from about 4.3 to 10 raised to power 14 hertz for red light. This is we're talking about light waves. And 7.5 to times 10 raised to power 14 hertz for violet light. Okay? So violet and red light are the opposite ends of the spectrum for the light waves. Okay? This is the lowest frequency and this is the highest frequency. Okay? So we know that light is not the only one of the electromagnetic waves, right? We know that there's ultraviolet light, there's gamma rays, X-rays. We know that there's infrared radiation and all the other types of radio waves, microwaves, etc. So those are all part of the electromagnetic spectrum. So we know that characteristic properties of all waves is that they obey the principle of superposition. Okay? So what we know about superposition is that if we have two waves, for example, if we have two waves that like over here, I don't need to draw it here because we have a diagram over here. We have two waves, one is like this, okay? One is like this. If we add them together, there will be constructive and destructive interference. Basically, principle of superposition says that if like two or more waves of the same nature are traveling past a point at the same time, the instantaneous amplitude there is the sum of the instantaneous amplitudes of the individual waves. So as you can see over here, इस point यहाँ पे दोनों के amplitudes positive हैं, ठीक है? They're along the positive y direction, so there we will get constructive interference and they will add up to get this. यहाँ पे दोनों की negative है, so it will still add up, ठीक है? Because both of them are in phase. So where they're out of phase, like for example, यहाँ पे line है, यहाँ पे it's 0 and 0, that will also add up to get 0. ठीक है? And then where do we get destructive interference? When they're out of phase, ठीक है? And at any point, if you can find that they're out of phase, because these ones they have some phase differences, ठीक है? They don't seem to be coherent, ठीक है? So this we know about the principle of superposition is that amplitudes are going to add or subtract based on their there will either be we'll just have to add the instantaneous amplitudes of the individual waves, and basically there will be either constructive or destructive interference. Constructive when there's a reinforcement of waves with the same phase to produce a greater amplitude, but destructive interference will be when there's partial or complete cancellation of the waves whose phases differ. ठीक है? उनके phase difference जब phase में जब difference आएगा, ठीक है? Then if they cancel out each other, or if partially or completely cancel out each other, then we will get destructive interference. So that is one of the properties of waves. And then we have diffraction as well. These are things we already know about. I'm just giving a brief review about these things, and then we're going to go and then we will do the black body radiation, जिसमें हमारे पास calculations आएंगी. ठीक है? So diffraction, we also know that when this is the diagram for diffraction, that if we have a monochromatic light source, meaning that all the light from that source is coming at the same frequencies, and ठीक है? So we will, if we have a slit, then it's going to go out of that slit and spread out, and then when it spreads out, it's just going to, like, we'll see that this light wave and this light wave, they reach another two further, they reach further two more slits. ठीक है? यहाँ पे एक slit है, it spreads out to diffracts. यहाँ पे दो और slits हैं, they will further diffract from here as well, spread out. And then जो diffraction की waves हैं, diffracted waves हैं, from this one and from this one, they're going to interfere with each other. So here we might get, if we place a screen over here, we will notice that some places there will be constructive interference, which are bright lines. This is the appearance on the screen, ठीक है? And some places there will be destructive interference, which will produce these dark lines. So as we said before, the destructive interference is where the amplitudes are subtracting out, canceling out, and the constructive is where they're adding. ठीक है? Then diffraction, we already know we've done the Young's double slit experiment in spherical astronomy. जिसमें we have, and in astronomy, I think we also did it in, we did the Bragg's law in this course also, and we also did, we've done Young's double slit experiment before as well in other courses. So basically it has to be this, the path length of the two slits differ by an odd number of wavelengths. ठीक है? We know that d sine theta is equals to m lambda. That is the condition for what? D sine theta is equals to m lambda is our condition for constructive interference, I believe. Where if the phase difference differs by an integer number of wavelengths, that will be constructive interference, and if the path difference varies by odd number of half wavelengths, ठीक है? That will be the destructive interference occurs. So that was about diffraction. So we don't have to go that much into the details because we've already studied, everyone already knows what diffraction is basically, ठीक है? And we've studied about Young's double slit experiment in previous courses as well. So today our main topic will be black body radiation, ठीक है? What do we know about black body radiation? Only quantum theory of light can explain what black body radiation is, ठीक है? So there was something different, and there's something different in black body radiation. It's not the same as electromagnetic waves, ठीक है? So we are familiar with the glow of a hot piece of metal which gives off visible light whose color varies with temperature. Okay, so basically if you have a very hot object, ठीक है, a hot piece of metal, for example, it's going to give off some amount of, it's going to give off some radiation, ठीक है? That radiation is called black body radiation. And all objects radiate energy continuously, whatever their temperatures are, ठीक है? So like it doesn't have to be so perfectly, like we will talk about what a perfect black body actually is, ठीक है? A perfect black body is one that will, an ideal body, it is convenient to consider as an ideal body one that absorbs all radiation incident on it regardless of frequency, ठीक है? That is called a black body. A black body is an ideal body that will absorb all the radiation incident upon it, regardless of what the frequency is, ठीक है? Regardless of what the frequency of the radiation incident upon it is, ठीक है? So that is a perfect black body, and we can we're going to discuss the mathematical aspects of how do we give some equations to the black body radiation, and how do we give it some values. Okay, so we're going to discuss that in this chapter. So what we're saying here is that we can create an idealized black body in a laboratory, and a black body can be approximated by, if you can see this diagram over here, okay? It's a bit small, but I hope you can see it. So it's like in a laboratory, a black body can be approximated by a hollow object, okay? ये एक box है, ठीक है? A hollow object, a hole in the wall of a hollow object. This is an object that is empty from inside, ठीक है? We have a small hole over here that leads to its interior. We have an incident light ray that's coming into here, and then it's going to enter the black body, and then it's going to radiation will strike the it's going to reflect back, it's going to be absorbed and reflect back, okay? So why is this like a perfect black body? Why is this like a black body? So yeah, so why is this an example of a black body? Because any radiation that enters the cavity, it will be reflected back and forth until it is absorbed, okay? So it will be reflected here and here and here. Some will be absorbed, some will be reflected, and then when the reflected ray will reach the other wall, and then some will be reflected, some will be absorbed, until it keeps on getting absorbed, partially absorbed and reflected until a point comes where it's all absorbed, okay? So basically until it's absorbed. So the cavity walls are constantly emitting and absorbing radiation, and it is the properties of this radiation that we are interested in. So the cavity walls are they're emitting and absorbing radiation. These walls, the walls of this cavity, are constantly emitting and absorbing radiation, and this makes it a good black body, okay? So in the lab, we can create a black body like by doing this example, by this apparatus and experimental setup. So what does the spectrum of a black body actually look like, okay? So it looks something like this, and we have done this in astronomy and astrophysics before, that there's a peak in the black body spectrum, okay? So we want to be able to give it some formulas. So we want to be able to so that's what we're going to derive, okay? Some formulas for the black body radiation. So black body radiation, its spectrum, it looks something like this. So there's a peak in the spectrum, okay? So it's over here on the y-axis, we have spectral energy density, which is given by, this is quite small actually, which is given by U as a function of frequency times du. That's the spectral energy density. Okay, and that we'll be mentioning that in the energy density will be coming over here. Okay, यहाँ पे हम इसकी quantification करेंगे. And then on the right, on the x-axis, we have frequency. So this is obviously a function of frequency, right? Spectral energy density is a function of frequency. So it makes sense to plot the spectral energy density on a graph of the energy densities versus frequency, because this depends on the frequency as well. So as you can see that यहाँ पे हमारे पास temperatures, these are two curves at two different temperatures, ठीक है? So we can see that black body radiates more when it is hot than when it is cold, ठीक है? यहाँ पे हमारे पास lower temperature and temperature of 1200 kelvins, यहाँ पे हमारे पास temperature 1800 kelvins आ रहा है. So what is the difference between these two is that the spectral energy density is obviously higher when the spectral energy density is obviously greater when it is at a higher temperature, when the black body is at a higher temperature than when it is at a lower temperature. Okay? So has this peak, and you can see also that the peak of the radiation, the peak of this curve is the curve becomes more like the peak of the curve is going towards the right. Okay? Like it has its peak, a hot black body has its peak at a higher frequency than the peak of a spectrum at a cooler one. Okay, so the spectrum of a black body is shown in this figure for two temperatures. So we now want to figure out why does it behave like this, and what is the equation for the black body radiation. So we have something, first we want to now go to a derivation of that. So let's see, we are going to do, we have examples to do as well. So we will go into the derivation of this. So the question now that we want to ask is, why does the black body spectrum have the shape shown in this figure? Why does it behave like this, okay? That with increasing temperatures, it's with the higher temperature, it has a higher peak, and the peak is shifted also towards the right, okay? Why does that happen? So we want to figure out exactly why. So the problem was examined at the end of the 19th century by Riley and Jaynes. They're two scientists, physicists. They were trying to understand this black body radiation. So the details, they started considering the radiation inside a cavity of absolute temperature T, whose walls are perfect reflectors. So what they did was they considered the radiation inside a cavity of absolute temperature T, Cavity का जो temperature है, it has a temperature of T, whose walls, absolute temperature T, whose walls are perfect reflectors. This is a three-dimensional okay, well, so basically what they said is that if we have, so basically we would be, whose walls are perfect reflectors, to be a series of standing electromagnetic waves. Now we'll be talking about concept of standing electromagnetic waves here, okay? Whose walls are perfect reflectors to be a series of standing electromagnetic waves, okay? We already talked about standing electromagnetic waves before, standing waves before. We did this in some potential welds chapter, okay? Quantum mechanics also. And we did this in previous chapters, that we have standing waves where there's a certain number of nodes, and we can write down equations of the lambda in terms of the L, okay? Where L is the width of the box, okay? If we have a cavity whose walls are perfect reflectors consisting of standing waves, okay? So perfect reflectors. Now, why are we considering these standing waves? Basically, why are we considering standing waves is because these two scientists, they consider the radiation inside a cavity of absolute temperature T, whose walls are perfect reflectors. The radiation inside this cavity was basically a series of standing electromagnetic waves. Basically, the radiation in this cavity is in the form of standing waves, okay? The black body radiation inside a cavity is in the form of standing waves. And when we have, if the box has, if the cavity has a length, width, you can call this the width of the box, okay? It's L. And then we have the wavelength, which is the lambda of the waves, of the standing wave. Then obviously this is half of a wavelength, right? L over here is equals to lambda by 2. Therefore, we would get lambda is equals to 2L. In this situation, we have lambda is equals to L because one perfect wavelength is equivalent to this length L. Over here, we have lambda is equals to 2 over 3 because 3 by 2 times lambda is equals to L. That's why we have this, okay? So why are we considering standing waves here? It's because the black body radiation can be seen to be a series of standing electromagnetic waves. This is a three-dimensional, the condition for standing waves in such a cavity is that the path length from wall to wall must be a whole number of half-integer wavelengths. As you can see over here, is that if we have, what is the condition for standing waves is that this lambda over here, the path length from wall to wall, which is this L, it is a whole number of half wavelengths, okay? Like over here, we're saying that L is equals to lambda by 2. Over here, it's just equals to a whole number of half wavelengths. So this can be considered as lambda by 2. 1 times lambda by 2. This can be considered 2 times lambda by 2. 2 and 2 will cancel. This will be considered as 3 lambda by 2. So basically, a whole number times lambda over 2 will be equal to L. So that our condition for the standing waves is that L will be equal to a whole number time, which can be 1, 2, 3, etc., times lambda by 2, a whole number of half wavelengths, so that a node occurs at each reflecting surface, okay? At each reflecting surface, we will get a node. So basically, the number of independent standing waves, G times G nu, D nu in the frequency interval. So between nu, what is nu here? Nu is frequency. Again, don't confuse that with velocity. because nu is not velocity, it is frequency. So the number of independent standing waves g nu, d nu in the frequency interval between v nu and d nu per unit volume of the cavity turned out to be this. So basically, Rayleigh and Jeans, we're not going to derive this formula, but they came up with this formula. Okay? Rayleigh and Jeans, they came up with this formula that the number of independent standing waves is given by this formula per unit volume in this interval d nu, which is an interval of a frequency. Okay? So they determined that it's given by this formula. The formula is independent of the shape of the cavity, ठीक है? As we would expect, the higher the frequency, इसमें हम क्या expect कर सकते हैं कि अगर frequency ज़्यादा है तो obviously we would get a higher number of standing waves in the cavity. Frequency ज़्यादा होगी मतलब है कि lambda कम होगा ना? Lambda कम होगा तो how many if lambda is smaller, then we would get a greater number of possible standing waves. Lambda अगर कम होगा, so how we can relate that to this? The higher the frequency of the wave, the shorter the wavelength and the greater the number of possible standing waves. ये क्यों होगा हमारे पास इस तरह से? Obviously, इस formula में अगर हम देखें तो frequency अगर ज़्यादा होगी, so the number of standing waves in the cavity will also be larger. Makes sense, right? Because frequency is the number of oscillations per time, right? So obviously, the greater the frequency, the shorter will be the wavelength, yeah, and the greater the number of possible standing waves. Because ये काम होता जाएगा ना, ये lambda काम होगा तो for this given wave, for this given length L, अगर lambda काम होगा, so there would be more higher frequency, so there would be more number of waves. So that makes sense. ठीक है? So now the next step to do is that what we want to do for the black body radiation, we said that black body radiation can be considered to be consisting of standing waves, ठीक है? Electromagnetic standing waves. So we're saying the dense number of standing waves in a cavity is given over a frequency interval is given by this. What we want to do is we want to find the energy. First, we want to find the average energy per standing wave, then we will multiply by the total number of standing waves in the cavity so that we can find the total energy radiated by the black body. Is that making sense? Okay, basically, हमारे पास standing waves in the cavity, this is the total number per unit volume of the cavity, total number of standing waves per unit volume of the cavity within a frequency interval d nu. And we want to find the average energy per average energy per standing wave, and then we will multiply them together. We will multiply the average energy per standing wave, which is given by this formula. We will multiply it by the number of standing waves per unit volume over this frequency interval, and that would give us the total energy per unit volume in this frequency interval. So basically, that is what we want to do here. So now what we want to find is that Rayleigh and Jeans, we want to see what Rayleigh and Jeans did to come up with an equation for the average energy per standing wave. Uska, what is the average energy per standing wave? Let's see what Rayleigh and Jeans came up with. So we want to find now what Rayleigh and Jeans did was actually not entirely correct, and we're going to come to the improvement of that in the next slides, which is the Planck radiation formula. That was the actual that Planck radiation formula is the correct one, which is what we're going to come up in the next few slides. But this is we're going to talk about what Rayleigh and Jeans did. Then we will see how it was improved later by Planck's radiation formula, and so we will get the final black body radiation formula. So the next step, so we're still doing what Rayleigh and Jeans did. So this is not entirely correct, but we are going to see what the improvement is in the coming slides. So basically, now what we want to do is, once we have found the number of standing waves in the cavity per unit volume over a frequency interval, what we want to do is we want to find the average energy per standing wave, then we'll multiply it by the number of standing waves per unit volume in the frequency interval. So now have you studied about statistical mechanics before? Any one of you? Do you know about the theorem of equipartition of energy? Okay. If you don't know about it, we'll just talk about that right now. The theorem of equipartition of energy, which is a part of classical physics, okay? Which states that the average energy per degree of freedom of an entity, such as a molecule of an ideal gas that is a member of a system of such entities in thermal equilibrium at the temperature T is half kT, where T is the temperature of the body of the entity, okay? For example, if we're considering a molecule of an ideal gas, then the capital T here is the temperature of the ideal gas, and K here, small k, is the Boltzmann constant, which is given by this number here. So what do we mean by the theorem of equipartition of energy? It says that the average energy per degree of freedom. Now we have to define what do we mean by a degree of freedom of an entity, such as a molecule of an ideal gas, for example. What do we mean by a degree of freedom? So let's see what that is, and then we'll come back to this one. So for example, if you have a monatomic, what do you mean by monatomic? Ideal gas is like one that has one molecule that consists of one atom only. Diatomic ideal gas means a diatomic ideal gas molecule means a molecule that has two atoms combined together. Okay? You have higher orders as well, diatomic, triatomic, etc. Okay? Like for example, a monatomic ideal gas. A monatomic ideal gas has 3 degrees of freedom because it only consists of one atom. Okay? Each molecule consists of only one atom, corresponding to why does it have 3 degrees of freedom? Because that corresponds to kinetic energy of motion in 3 independent directions. Because the motion of the molecule can be in 3 independent directions. What do we mean by a degree of freedom? Means the number of independent entities, the number of independent variables that are there in that system. Okay? So what I mean by degree of freedom here is that it corresponds to the kinetic energy we have for monatomic ideal gas. We have 3 degrees of freedom. Why? Because that corresponds to the kinetic energy of motion in 3 independent directions. Its velocity of that, the velocity of that monatomic ideal gas molecule can be in 3 independent directions, right? Like if we have the x and the y and the z component. This is our x direction, this is our y direction, this is our z direction. So the velocity of the one atom, its velocity, if it's like something like this, it will have 3 dimensions. It will have 3 components of its velocity in the 3 dimensions, which results in 3 independent kinetic energies. If you consider all the 3 velocities separately, you can add the kinetic energy. Total kinetic energy will be the sum of all those 3 components. Together will be the total. So if you have 3 independent degrees of freedom, and we're saying the theorem, wait a minute. First, before I go back to the theorem of equipartition of energy, I want to mention that one-dimensional harmonic oscillator. Do you know what a harmonic oscillator is? It's like we have, and quantum mechanics, we did this in quantum mechanics a little bit, but basically we didn't finish it because there were some mistakes in the book regarding the harmonic oscillator. If you have a wall and you have a spring, okay? This is and you have a mass attached at the end of that spring. So this is an example of a harmonic oscillator where you have, this is our equilibrium position, and then if you apply a force that is going to pull this spring away from its equilibrium, then we will have a restoring force in this direction, okay? Where the restoring force is given by the equation minus kx. Because it's going to want to bring it in, it's going to want to pull it along the negative x direction, and k here is what? The spring constant, okay? So this is an example for harmonic oscillator. And how many degrees of freedom does this system have? It has 2 degrees of freedom. Why? Because one corresponds to its kinetic energy. It's a one-dimensional harmonic oscillator, by the way. It cannot move in 3 dimensions. So 1 dimension will be for this kinetic energy, which will be the motion along the straight line. The kinetic energy will be calculated by its instantaneous velocity at any particular point. Okay? plus its potential energy at its point. The total energy, so there are 2 degrees of freedom for a harmonic one-dimensional harmonic oscillator, one corresponding to its kinetic energy, one corresponding to its potential energy. So we have 2 degrees of freedom here. So now these are 2 examples of 2 situations, okay? And if you have a diatomic ideal gas, that should have 6 degrees of freedom because it has two atoms in one molecule, and each atom has 3 degrees of freedom. So you would have 6 degrees of freedom. So basically, the theorem of equipartition of energy says that for each degree of freedom of an entity, such as a molecule of a gas or a harmonic oscillator or whatever, you have to multiply the average energy per degree of freedom is going to be equal to half kT. Okay? So half kT is per degree of freedom. So as you can see that in this system over here that we have a monatomic ideal gas, there are 3 degrees of freedom. So you have to multiply half kT by 3. If you have a diatomic molecule, you will multiply half kT by 6. If you have a harmonic one-dimensional harmonic oscillator, you will multiply half kT by 2. Because basically this half kT is the number of degrees of freedom you have per is the average energy per degree of freedom of an entity. ठीक है? So यहाँ तक I hope you understood that. So now we're saying here is that each standing wave in a cavity originates in an oscillating electric charge. Basically, we're talking about the standing waves in a cavity that we just mentioned over here, that the black body radiation can be assumed to be like standing waves. Okay? So standing waves in a cavity, we have oscillating electric charge in the cavity wall. So 2 degrees of freedom are associated with the wave. So we have 2 degrees of freedom, oscillating electric charge in the cavity wall. Why do we have 2 degrees of freedom in this system? इसमें 2 degrees of freedom क्यों है? क्योंकि we have one end of the wall is here, one end of the wall is here. These are like two independent variables. Are like this distance L is defined by this point over here, which is 1 degree of freedom, and this point, which is the other degree of freedom. So you have 2 degrees of freedom here. Like degrees of freedom, you can understand that basically in terms of the number of independent variables you have in the system. Okay? So here we have 2 degrees of freedom. So basically, it should have an average energy of 2 times half kT. So the 2 and the 2 will cancel, and we will get kT. So the average energy per standing wave is kT. So now this is a classically, Rayleigh and Jeans determined this according to the classical physics, and later we will find that Planck determined something else which was a bit different from this, and that was Planck's one is the correct one. So Rayleigh and Jeans said that the total energy U as a function of frequency times over an interval of d nu, which is our frequency interval from nu to nu plus d nu, and this is also the total energy per unit volume, is therefore going to be given by the number of standing waves per unit volume in an interval d nu times the average energy per standing wave. That will give you the total energy per unit volume in the cavity in this frequency interval. So when we multiply this equation that we had over here, इस equation को हम इस equation kT से multiply कर देंगे, we will get this equation. Yeah, this is not a negative sign, this is an equal to sign. ये equal to का sign है, ये negative नहीं है. So we will get now this equation. So what we're saying here is that the radiation rate is proportional to this energy density for frequencies. So if this is the total energy per unit volume in the cavity, this is like the total energy per unit volume in the cavity for this frequency interval d nu. So the radiation rate of the black body will be proportional to this energy density for frequencies between nu and v plus nu plus d nu. So in this frequency interval, the black body radiation rate will be proportional to this energy density, जो हमने अभी determine किया ये. This equation 2.3, ये equation जो है, this is known as the Rayleigh-Jeans formula. It contains everything that classical physics can say about the spectrum of black body radiation. So this, according to classical physics, This is the formula for, this is the called the Rayleigh-Jeans formula, and this is the formula that tells us, that contains everything that what we can say about the spectrum of black body radiation classically. However, we said that we can see that this formula cannot be entirely correct, cannot possibly be correct. Why? Because as the frequency nu increases towards the ultraviolet end of the spectrum, what would happen to the energy density? The energy density should increase as nu squared. You can see that the energy density is proportional to nu squared. So then in the limit of infinitely high frequencies, if the frequency goes infinitely high, the energy density would also go to infinity. And reality, energy density falls in reality, energy density and radiation rate falls to 0 as nu goes to infinity. Figure 2.8. Like, I'll show you this figure over here, that Rayleigh-Jeans, according to Rayleigh-Jeans formula, the graph of the spectral energy density versus frequency curve would be like this. But the observed one is actually, observed black body radiation is actually like this. Okay? So this will be determined by experimentation and by observations. ठीक है? ये जो graph हम यहाँ पे हम, this is the Rayleigh-Jeans ने तो ये कहा था, ठीक है? According to the Rayleigh-Jeans formula, we would get this curve, but the observed curve that we actually get by experimentation is this, like this. So there's obviously some discrepancy here, ठीक है? This discrepancy became known as the ultraviolet catastrophe of classical physics. इसको हम ultraviolet catastrophe कहते हैं. So now we want to figure out, where did Rayleigh and Jeans go wrong? How do we figure out how to improve this formula, ठीक है? So now we will talk about, in 1900, we will talk about the Planck's radiation formula, whereby in 1900 the German physicist Max Planck used, he came up with a formula for the energy density of a black body radiation, ठीक है? And basically Max Planck, जो scientist था, he came up with a radiation formula for the spectral energy density of black body radiation. He came up with this formula, ठीक है? And here H over here, यहाँ पे H addition है, ठीक है? Basically यहाँ पे H नहीं था, ठीक है? Planck ने H, this is the Planck's constant, by the way. We already know this is the Planck's constant, ठीक है? So he added this constant into this formula, and he also changed it a bit by, यहाँ पे, if you look at this formula versus this formula, there's some exponential factor over here, -1, ठीक है? And also here, this was proportional to nu squared. Here's proportional to nu cube. So basically, we don't need to know how to derive this formula, but we will say that Planck came up with this formula, and we want to see now whether this formula will seem to be correct or not. Let's see now. So basically, now we want to see if this formula, if Planck's formula will be correct relative to the Rayleigh-Jeans criteria, ठीक है? So what we can say is that at high frequencies, h nu will be much greater than kt, ठीक है? High frequency में h nu, क्योंकि nu frequency है ना यहाँ पे, तो h nu will be much greater than kt, and basically this term over here, which is e power h nu over kt, it goes to infinity. So basically this term over here, as the frequency, remember we said over here that as the frequency for the Rayleigh-Jeans formula, as the frequency goes very high to infinity, this energy density will also go to infinity, which should not be the case. It should not go like this. It should in fact go to 0. So so over here, this exponential correction, we can call it like a correction, which works for us because as nu goes to 0, as nu goes to frequency which is very high, like infinity, then this term will also go to infinity, which means that if we put infinity back in this formula, we will get 0. So it works here for us. Then the energy density would go to 0 as observed. So we don't have any ultraviolet catastrophe anymore. ठीक है? So at low frequencies where the Rayleigh-Jeans formula is a good approximation to the data, Rayleigh-Jeans formula can be a special case of this. Rayleigh-Jeans formula can be a special case of this for this classical physics, ठीक है? But it won't work at very high frequencies. So where the Rayleigh-Jeans formula is a good approximation to the data at low frequencies, ठीक है? Low frequencies में the Rayleigh-Jeans formula can be a good approximation, but at high frequencies it's not going to work. We have to use the Planck's radiation formula. So for the low frequencies, h nu is much less than kt, and h nu over kt will be much less than 1. h nu, ये kt को यहाँ से divide कर दें, तो h nu over kt will be much less than 1. So we also know the Taylor expansion of exponential is given by this formula, ठीक है? इसका exponential e power x का Taylor expansion इस तरह से दिया जाता है. So if x is very small, which we're saying we're talking about very small frequencies here, okay? Very small frequencies means that this x here, which we can consider to be h nu over kt, it'll be very small. So this becomes approximately 1 plus x, okay? For very small x. So when h nu over kt is very small, the 1 over e power h nu over kt minus 1 will be approximately equal to 1 over this term over here will be approximately equal to 1 plus h nu over kt, which is this thing, minus 1. So 1 cancel. This will be equal to kt over h nu. So so at low frequencies, Planck's formula would just become, at low frequencies, Planck's formula, if you put this 1 over e power h nu over kt minus 1 is equal to kt over h nu for in place of this thing over here, 1 over e power h nu over kt minus 1, then we would basically get, it would reduce, the Planck's formula reduces to the Rayleigh-Jeans formula. So Planck's formula is clearly at least on the right track, if in fact it has turned out to be completely correct. So the Planck's formula is completely correct because the Rayleigh-Jeans formula is not entirely wrong. It works for classical physics and for the case where the frequencies are small, low frequencies, okay? When we have high frequencies, then we have to use the Planck's radiation formula, basically. Okay? Are there any questions so far? Example, we have an example as well, and we also have what else do we have to do here? Oscillator energies, actual energy. But yeah, are there any questions so far? So I think we're out of time right now. So I think we will continue. We will do this example here, and we will do this slide from slide number 20. There are actually only 3 more slides in this chapter. In this not this chapter, but in this topic. We have 3 more topics within this. We have 3 more topics within this chapter, which is photoelectric effect, which will be after black body radiation. We have X-ray diffraction, Compton effect. Okay, so we have to do these topics as well. So today is what? Today is 14th, so we have a quiz on the 16th. Then 15th, 21, 22, we will have 3 more lectures. I hope that we'll be able to finish this particle properties of waves in 3 more lectures. And then 23rd will be the last quiz. 23rd will be 1 quiz, and 28th another quiz, possibly. Okay. For now, we're sure that we have 2 quizzes, 16th and 23rd. 28th, I might have to go to IST for like some work, so we will see if the quiz should be on 28th, or maybe if we can try to make it before the 28th, that would be better, so that I can, because on the 28th I have to go there to input all the marks and attendances and everything, so it might be difficult to have the quiz on the 28th, but in that case maybe we can have instead of 28th we can shift the class to maybe Friday or Thursday that same week maybe, but then we have a quiz on 23rd, so I'm not sure about this quiz. I will see what we can do about the last quiz, which is right now supposed to be on the 28th, because I have to go to IST on the 28th for maybe the whole day. So we will see if we can shift the quiz like 25th December, if it's possible. Tika? Are there any questions? Let me download the attendance list as well. Okay, so yeah, this was about black body radiation, and we will just finish this next three slides, and then we will do photoelectric effect, which is over here. Particle properties of wave, lecture 10. This one, particle properties. This is for the photoelectric effect, ठीक है? फिर ये हम कल कर लेंगे, और ये जो हमने अभी किया है ये 3 slides भी हम कल कर लेंगे, फिर 16th को quiz है, ठीक है? फिर we will see about the last quiz, when we can keep that last quiz. Ideally, it should be before the 28th, so that I can also check it and upload the marks on 28th, ठीक है? But does anyone have any suggestion about the last quiz? Or maybe we, because we have a quiz on 16th, we have one on 23rd.
Can we skip the last quiz?
That's also possible, but then we would have total, that would be 6 quizzes, and then count the best 4 or 5.
4. If you have 6 quizzes, you can count best 4 of it. Can you?
That's also possible. I will think about it, what we can do, because before we, then that means that the last topic, particle properties of waves, का कोई quiz नहीं होगा फिर. Okay, I'll see what to do about that, okay? Because on the 28th, I have to go to IST and enter all the marks and sessional marks and all the attendances, and I have to do other things as well. So it might be difficult to have the quiz on the 28th, but I'll see about that, okay? If we need a quiz, the 7th quiz or not. And I mean, it will still be in the final exam, so particle properties of waves will still come in the final exam, but I will see if we can have another quiz or 5th, 7th quiz or not, okay? Yeah, I think that's all for today. ठीक है? Does anyone have any issues or questions or anything to discuss? No? Okay, then I think we can call it a day now, and we will continue tomorrow. ठीक है? Allah Hafiz.
Allah Hafiz, ma'am.
Allah Hafiz.